It is chapter 1, linear equations. In this chapter, we'll study basics of linear equations, including systems of linear equations, three-element row operations, and linear transformation. Let's go to the first section, section 1.1, systems of linear equations. By definition, a linear equation in the variables x1 to xn is an equation that can be written in this form: a1x1 plus a2x2 and plus here anxn equal b. Here b is the right hand side and a1 to an are the coefficients, and it can be real or complex numbers. But in this class, we'll deal with mostly real numbers. A system of linear equations, or simply a linear system, is a collection of one or more linear equations involving the same variables, say x1 to xn. And part A here is a linear system having two variables, x1, x2, and right side, this is a linear system of three equations of three variables, x, y, z. A solution of a system is a list S1 to Sn of numbers. So it's an array of numbers that makes each equation a true statement. That means that solution is an array of numbers that satisfies all the equations. The solution set is the collection of all possible solutions of the linear system. If you have two linear systems and if they have the same solution set, then we say the two linear systems are equivalent. For example, from part A here, we replace the first row, first line, first equation by first equation subtracted by second equation. Then that will be 2x1 and minus 4x2 equal minus 2. That is the equation replaced. Here, this system and that system will have the same solution, so they are equivalent. Okay. Linear systems may have no solution, exactly one solution, and infinitely many solutions. For the case of exactly one solution, we say the unique. The solution is unique. Once the system has no solution, then we say the system is inconsistent. Either one or infinitely many solutions exist, then we say the system is consistent. Let's consider the case of two equations and two unknowns. Okay, here, part A. Okay, to see the system of equations more clearly, let's try to write down them into form you learned from high school. So that is y equal x plus 1 for the first one. The second equation, y equal now x plus 3. Now you learned these equations from high school. Okay, that xy coordinate system, the first equation is now y equal x plus 1. Oops. Okay. Okay, let's try to make it again. Y equal x plus 1, passing this 1, slope 1, and here 3, so y equal x plus 3, that is a 3. So these two lines are parallel and they cannot meet each other. So there is no solution. For the second one, if we write the same way, then that is now y equal here minus x plus 1. And second one, from second one, we can see y equal x minus 2. Right? So one has a slope minus 1, the other one has a slope plus 1. So they should meet each other at a single point, which is the intersection, and that makes the solution. So it has a unique solution, right? Now for the final one, once the first equation is multiplied by 2, then it becomes the second one. It's twice, twice, twice. So basically, we have two equations, however, they are the same, so that if you try to make a graph for each one, then the graph will be overlapped, identical to each other. So that if you consider solution, then there will be infinitely many solutions. And either these two cases is consistent. If there is at least one solution, then it is consistent. And if it has no solution, then it is inconsistent. Okay? When we are dealing with linear systems, there are two fundamental questions. The first one is existence, and the second one is uniqueness. Through existence, we can ask a question like this: is the system consistent, or does at least one solution exist? Such a question is existence questions. For uniqueness, we can ask if a solution exists. Is it the only one? Is the solution unique? When you are dealing with linear systems using computer programs, then in many cases, uniqueness and existence and uniqueness is not guaranteed, then the computational algorithm may break down. So that in most cases, when you are solving the problem by using computers, then the system should have unique solution. And also in reality, most systems in real world are consistent, and they produce the same output for the same input. That means the solution is unique. And existence and uniqueness are guaranteed for most systems in the real world. Okay, now let's begin with how to solve linear systems. Here first we'll try to rewrite the linear system into matrix form. For example, we have two equations, and from this one, we can write this system into this matrix form. Here we collect coefficients x here minus 2, 3, 1, and 2. That is becomes here coefficients matrix, and x1, x2 unknown, and minus 1, 4 the right side. So once we write down in this way, then many cases is much more convenient and effective. Here, in this system in matrix form, the essential information is along with this coefficients matrix and right side. So we collect them into this augmented matrix. The first two columns is from coefficients matrix, and now the last column is coming from the right side. Sometimes we put here the vertical bar to indicate that this is from coefficients matrix and that is from right side. But sometimes we ignore this vertical line. So this will include the essential information of the given linear system. Okay? Now, to solve the problem, to solve the linear system, we'll use elementary row operations. There are 3 elementary row operations. You learned this from your high school, but we consider it more systematically. The first one is replacement. Replace one row by the sum of itself and a multiple of another row. Here, when we are considering equivalent system, we did it here. Now, first row is replaced by first row itself, and here added by -1 times the second equation. We did it here. So that is a kind of replacement. Now, the second one is interchange. Just simply change the row, and ith row and jth row changed. And scaling, we multiply the whole row by a non-zero constant k. Just simply ith row is now replaced by k times the ith row. That is scaling. These elementary 3 operations will be used for solving linear systems, and these operations will be used all the way through the class by the end of the semester. Okay, now let's try to use these operations for solving this linear system. Okay, first we collect the coefficients matrix, and -2, 3, 1, 2, -1, 4, the right side, we already did earlier. So that is now augmented matrix in representing this linear system. And here, for convenience, we try to interchange the 2 equations. So 2 will become 1, and equation 1 will become 2. So interchange, then now we can recheck that one. Here in matrix form, we simply interchange 2 rows. Here we interchange the equations 1 and 2 to become this one. Now here we interchange the row of numbers to make this one. Of course, if we try to get augmented matrix from this one, then you will reach this one. Now, we'll try to eliminate that one. And you learned this one from high school. If you add twice of a first equation to second equation, then that will be 0 here for x1, and twice added, so that will become 7x2, and twice, and 8 is added to -1, will become 7. The same way in metric form, twice is added to the second row, then that will become 0, and that will become 7. That will become 7. Of course, this augmented matrix is representing this system. Now, we make a scale. So 7 can be eliminated by multiplying 1 over 7. So it becomes x2 equal 1. The corresponding part is here. Just multiply 1 over 7 to make 1, 1. And now we will try to eliminate that one by subtracting twice of the second equation. Then here, twice of second equation, then right side for that one will become 2. But now x1, so that eventually x1 equal 2, x2 equal 1. In this system, again, same way, side the same way, twice of x2, twice of second row will be subtracted, then it will become 0, it will become 2. So that we reach at that one. So here we reach at this matrix representing that one. So it means that here x1 is 2, x2 is 1, right? And also this is on the identity matrix in 2 dimensions. So start with a matrix A here, and then by using elementary row operations so that we make this portion identity, then there's the last column will be the solution. Okay. 2 matrices are row equivalent if there is a sequence of elementary row operations that transform one matrix to the other. Here we see various matrices. These matrices are row equivalent because we reach these matrices by using only elementary row operations. So once you can transform from one to the other by using elementary row operations, then they are equivalent. Okay? So all are equivalent. Solve the following system of linear equations using the 3 elementary row operations, then determine if the system is consistent. Okay. From the linear system, let's collect coefficients and right side to make the augmented matrix. Okay, from this one. Now, there is 0 here. 0, 1, minus 4. Okay, let's write down the coefficients matrix first. 0, 1, minus 4, and 2. Minus 3 and 2 here, and finally here now 4, minus 8 and 12. The right hand side is 8, 1, 1. Okay. Okay. From here now we'll apply elementary row operations. First once it's 0, then it's not convenient, so that we may move this on the top. Okay, then there is 2, minus 3, so we apply interchange, minus 3, 2 and 1, and 0, 1, minus 4 and 8. Okay, and there's 4, minus 8 and 12 and 1. Okay, here we did now R1 and R2 interchange. Okay. Now we have to eliminate this one. 4. How? Just twice of R1 is subtracted from R3. So here R3 will be replaced by here R3 and minus twice of R1. Okay. Then other roots are the same. 2, minus 3, 2 and 1, 0, 1, minus 4 and 8. And then twice subtracted will make a 0. Twice subtracted, that will be 6 is added, so that is a minus 2. Twice subtracted, 4 subtracted, so that it will be 8. Now twice 2 is subtracted. Okay, twice subtracted, so that will make it here now 3. Okay, no, minus 1, right? Yeah, minus 1. Okay, now we'll try to, okay, later on we'll define this is a pivot, and also it becomes a pivot. Now we have to eliminate this row portion. How? Just twice is added. Then here 2, minus 3, 2 and 1, first and the second row will not be changed. 0, 1, minus 4 and 8, and then twice added, then 0, 0, 0, and last one is now 15. Right? Okay. Here we'll see, we'll try to interpret these rules. Okay, for the first row and the second row, yes, it'll be long, so that now we'll focus on the last row. Okay, that represents that 0x1 plus 0x2 and 0x3 equal 15. No matter what x1, x2, x3 are, the left hand side will be 0 and right hand side is 15. Is it possible? It's impossible. So that means that this system of equations has no solution. So the system is inconsistent. So we may stop here. Okay. Determine the value of h such that the given system is a consistent linear system. Okay. The same way, we begin with augmented matrix. Okay, here we first collect the coefficients 1, h, and right hand side minus 5, and 2, minus 8, and here 6. Right? From this one, now let's try to eliminate that one. Twice subtracted. So the first row will not be changed, and that is a minus 5. And second row will be 0, twice subtracted, so that minus 8 minus 2h, and twice subtracted, so that 10 is added, so that is 16. Right? Okay. Now here, once it is 0, if this one is 0, then again, exactly same way, we can say that now 0 becomes here non-zero. Here, that's 16. So that here, if this is 0, then we have no solution. So here, if it is non-zero, so that minus 8 minus 2h is not 0. Once it is satisfied, then now we can scale this row so that it will become 1 and it will become some number. And by using that, again, you can eliminate this h. Right? So for the choice of h, here non-zero, if this is non-zero, then you can scale is 1, and you can eliminate that, so you can have a unique solution. So here, once this is satisfied, then it will have unique solution. So it's consistent. That is exactly the same as here. H is not minus 4. Then it has a solution, but the solution must be unique. Okay. Here we have true or false problem. Every elementary row operation is reversible. Is it true? It must be true. The reason is, for example, for replacement is adding another row to a certain row. If you subtract the same amount, then it is inverse of the operation, right? So that every elementary row, every replacement is reversible. Also, interchange, if you do one more time, then it will go back to original 1. And for scaling, if you multiply k, then for the operation, if you multiply 1 over k, then it will go back to original 1. So that eventually every elementary row operation is reversible. So it is true. Okay. Now, secondly, every row operations on an augmented matrix never change the solution of the associated linear system. Is it true? Usually in true or false statement, once the expression is strong by using such a word never, then usually in many cases is false. But for this statement is true. Elementary row operations on the augmented matrix never change the solution of the system. Two linear systems are equivalent if they have the same solution set. Is it true? Yeah, it's true. From the definition, we defined that once the solution sets are the same, then they are equivalent. Okay. In mathematics, and always problem solving start with a definition. Okay. Two matrices are row equivalent if they have the same number of rows. Is it true? No, it's a stupid sentence. And just it is saying that the two matrices have the same number of rows, and it doesn't say about rows or any other things. So it cannot be row equivalent. Okay? Okay, this is the end of the section. Thank you.